In this presentation, we'll look at how carbon atoms form a wide variety of molecules. To start off, let's consider the shape of a single carbon atom. In a previous presentation, we considered the Bohr model of an atom. In that simple model, there were only round electron shells. Not surprisingly, the reality is more complex. We now recognize that within an electron shell, there are several orbitals, or space, taken up by the electrons. S orbitals are spherical, but some orbitals, called the p orbitals, have a dumbbell shape. When S and p orbitals hybridize together, the result is a tetrahedron shape. As a tetrahedron, the electrons occupy the corners of the tetrahedron and are thus as far apart away from each other as possible. When a tetrahedral atom, such as carbon, reacts with hydrogen to form methane, the hydrogen atoms also occupy those corners of the tetrahedron and are thus as far apart from each other as possible. The orbitals of oxygen also cause the oxygen to have a tetrahedral shape. When oxygen reacts with hydrogen to form water, the hydrogens occupy two corners of the tetrahedron. The remaining unshared electrons of the oxygen atom occupy the other two corners of the tetrahedron and therefore effectively take up space. It is this space taken up by the electrons that gives water its bent shape. Here's another look at that tetrahedral shape of methane. Notice that for convenience, when we draw a structural formula, we indicate the angle between the hydrogen atoms as being 90 degrees. However, that's a two-dimensional representation of a three-dimensional molecule. The true bond angle is about 110 degrees. To better represent this, we use a structural formula shown on the right, where the hydrogen atom with the solid triangle is coming out of the paper towards you, and the hydrogen atom with the dashed lines is going into the paper. Most carbon compounds have carbon single bonded to other atoms. When this is the case, the carbon forms a tetrahedral shape. However, carbon also forms double and triple bonds with other atoms, usually other carbon atoms. When this happens, it no longer has a tetrahedral shape, but instead is in the shape of a triangle, or is linear. To compare these three, let's start by looking at a single carbon atom inside the ethane molecule. Ethane has two carbon atoms joined by a single bond. Each of these carbon atoms has its neighbors arranged in a tetrahedral pattern, as we've already seen. Ethene, or ethylene, has a double bond between the two carbon atoms. As a result, there are only three atoms around each of the carbon atoms. These three atoms space themselves out maximally, resulting in a planar arrangement around each carbon atom. In fact, as you can see here, the final shape of the whole molecule is in fact planar. Ethine, also known as acetylene, has a triple bond between its two carbons. As a result, the two atoms around each carbon atom space themselves out maximally to form a linear molecule. The chains formed by carbon atoms covalently bonded together are highly varied. Hydrocarbons only have carbon and hydrogen atoms. Even for molecules that only have these two atoms, they can vary in the length of the carbon chain, how the chain may be branched, the position of double or triple bonds, and the presence of rings. Even among molecules that have exactly the same number of hydrogen and carbon atoms, there may be a number of different structures. Two molecules that have the same molecular formulae but different arrangements of the atoms are called isomers. Here we see structural isomers which simply have the carbon chains rearranged. Notice, however, that despite this rearrangement, both of the molecules have 5 carbon atoms and 12 hydrogen atoms. A less obvious form of isomers are what are known as cis-trans isomers. Like other isomers, they have the exact same molecular formula, but they have a different arrangement of atoms around a double bond. On the left, you can see that both blue X's are on the same side of the double bond, and remember that this molecule is planar. On the right, you can see that the two blue X's are on the opposite sides of the double bond. To understand the effects that this can have, it's useful to look at fatty acids, which we haven't studied yet in this course. On the top, we have a fatty acid that has all single bonds. It's known as saturated because it's completely saturated with hydrogen atoms. In the middle, we have a fatty acid that has a single double bond. This double bond is in the cis configuration. You can see that the two hydrogen atoms attached to the carbon atoms are on the same side of that double bond. The result is that the whole molecule is now bent or kinked at that double bond. In the bottom part, we have a trans fatty acid. You can see that the lone hydrogen atoms are now on opposite sides of the double bond in the trans configuration. The result is a fatty acid that is again almost linear. Now, you may have heard of the dangers of eating trans fats. Fatty acids are the main components of fats. Food companies regularly produce trans fats as part of their manufacturing process. However, they're not the natural form of fats and are the result of chemical rather than biological processes. Double bonds are manipulated in food products because they cause the fats to have different physical properties. Saturated fats tend to pack together very closely and are generally solid at room temperature. Unsaturated fatty acids, with their kink, do not pack very close together and tend to be liquid at room temperature, or oils. So food companies manipulate the double bonds in fats in order to make the fats have appealing characteristics. However, when we eat fats, we use an enzyme called lipase to break down the fats, and this enzyme does not work well on trans fats, resulting in health problems. Another even less obvious type of isomers are called enantiomers. Enantiomers are non-superimposable mirror images of each other. A good example of this is your left and right hand. They're mirror images of each other, but you can't superimpose your left hand on top of your right hand because they're not the same. To see how this effect works with molecules, imagine you're holding these two molecules in your hand. Now take your left hand and tip it so that your thumb pushes upward and the three large colored groups end up sitting on the table, with hydrogen pointing straight up at you. Looking straight down at it, you should see something like this. Now let's do the same thing with the molecule on the right, which is a mirror image of the first molecule. What you would find is that no matter how you rotate either molecule, they can't be superimposed because they're not the same. Now, it's worth noting that this only works for molecules that have 4 different groups attached to the central or chiral carbon atom. If 2 of the groups are the same, such as 2 hydrogen atoms, then they would in fact be superimposable, and they would be the same molecule. That's enough detail for now, but we'll look more at chiral molecules, particularly when we learn about sugars.